I'm Byron Johnson with Coordinated Power. Just going to walk you through kind of the philosophy of doing the ground grid design to mitigate the step and touch potentials that we talked about in the previous video. The first thing that we're going to need to obtain to do the study is going to be the soil resistivity, right? So it's going to be different at every site. What is the electrical properties of the soil? Now you can see in the picture what's typically done is it's the 4-pole winter test method. 4 probes are driven. You can see they're equidistant between them based off the A dimension in the lower left picture. The voltage is applied to the inner probes. Sorry, take that back. And current is injected on the outer probes, and the voltage is measured on the inner probes. And they're divided out, and they give you a resistance value. And there's an equation that will turn that resistance based off the probe spacing into a resistivity for the soil. And it's essentially measuring the soil as its entire collective makeup. You can see in the upper right picture there's an upper layer and a lower layer, and a lot of softwares divide the soil into 2 layers like that, and you find that you get a better match to the given soil by breaking it up into an upper layer resistivity and a lower layer. And at the boundary there's reflection effects, and it's actually really complicated math, but the various softwares solve it well for 2 layers, and then some go further into 3 layers, or maybe up to 10 or more layers. I think some even do vertical layers. Our software we use is typically WinIGS, and it will go up to 3 layers and 4 if you define them manually. So, all right, I'll keep going to the next slide. As I'd mentioned before, the probes are driven at equidistant spacing. So you can see here someone is out in the field. They've got the little yellow box hooked up to their 4 probes. This is a very close spacing. And then we walk the spacing out. We take one test here and we get one resistance value. And this measures the depth into the earth. I'll have to double check the exact equation for how deep you're theoretically measuring and monitoring based off your probe spacing, but it is directly tied to the probe spacing. So the further out you get your probe spacing for that A value on the previous slide, effectively the deeper into the soil you're taking into account. So what's typically done is you drive 4 probes like that, you take your measurement, then you pull up the probes and you go spread them out to a higher A value, a higher spacing. And we typically go all the way from the first measurement of 2.5, 5-foot spacing, 10-foot spacing, 20-foot, 30-foot, all the way out to 200 feet if you have that much room. And then oftentimes you have some risk if there's metallic objects buried in the soil that they'll throw your measurements off. So a lot of times to kind of work around that, you'll take a perpendicular. You'll do your first set of measurements where you string out your line and you'll increase your probes along that line, and then you'll start over and rotate your test 90 degrees and go perpendicular to your first test. That way, hopefully you can, if you were overly skewed in one direction, hopefully you're no longer parallel with it, and it'll skew your other set of measurements much less. All right, leaving the soil resistivity, the next thing that you're going to need is the fault current duration and the amount of fault current. Typically get that from the utility or whoever owns and supplies the incoming transmission to your substation or your site. So a lot of times if you have source impedance at the transmission interconnection, that's fine. You can use that to calculate the maximum ground fault current. But then you'll still need from the utility the trip time associated with that max ground fault current. And we base our studies off of the max ground fault current on the high side of the station. There's reasons for that we can discuss later, but for now we're going to leave it at you need the fault current and the duration. And the duration can be overcurrent protection depending on the upstream protection and control that's set. So it might be overcurrent. In that case, you need the trip value at the max fault current, and then add in the breaker operation time too. So you might have a 3 to 5 cycle breaker actual operation once it gets the signal from the relay as well. If you have just high-speed distance protection, maybe you're much faster and you're much closer to just that, a few cycles for the distance protection to actuate and get to the relay, and then 3 to 5 cycles for the breaker to operate itself. So the next topic is split factor. And basically the concept comes down to this. Your GPR event, ground potential rise, is entirely tied to how much fault current is going from the grid into the earth. So if you've got transmission static wires that are grounded as well, some of that fault current will return to the source on that static wire. Some of it will also leave on distribution feeders that leave your station and go out. They have a neutral wire that gets grounded periodically on every pole. So some of that fault current will go into the grid, but it won't actually go from the grid into earth. It'll go from the grid into the neutral conductors and down the distribution lines, and some of that current will disperse back into earth on those distribution grounds, and some of it will go back on the transmission static that's also grounded. So you can see here in substation A in the picture, you have some of the current is grid current, and some of it is returning on the earth wire. So all of it comes on the phase wire that's faulted, and on the earth wire, some of it goes down. Some of it might go all the way down the wire back to the source, but then some of it also splits and goes back on the tower grounds along the way. So we need to come up with that max fault current and ultimately the split factor, which is how much goes into the grid. And it turns out to be a function of, the connections that you have, how many static wires, earth wires you have, what the impedance of their tower grounds are, and how many distribution lines you have, and how many, what's the resistance that you get on the pole grounds for those, and the resistance of the grid itself to earth. So depending on, basically those are all the parallel paths that the fault current can go on. IEEE Standard 80 has these split factor tables that are very helpful. You can model it. You can model in your software incoming transmission lines. You can model the actual neutral they return on and all the tower grounds and all the distribution lines, and you'll get a very calculated split factor because the software knows the grid resistance and all of those others. You can also use the IEEE split factor tables. So this, and this is one of many tables. So they have a table for 100 ohm and 200 ohm, 100 ohm transmission grounds and 200 ohm distribution grounds. But they also have tables for 25 ohm distribution grounds and a number of tables that have different arrangements of this data. But it's generally you pick. The slash here means one transmission line and one distribution line connected to your station. So then you can if you know your grid resistance and your one transmission line, one distribution line, you can then read off over here on the left is the percentage of split factor. So it's, you read that off the chart to get your percentage split factor to tell you how much current goes into the grid versus what is returned in other means, right? And then we only do our grounding study based off the actual grid current and the touch and step potential that it produces. Then just to wrap us up for this module, some of our typical design parameters for a substation ground grid that we're designing would be, we like to use 25 ohm meters for a 6-inch rock layer. We'll put a 2-aught copper loop around the fence on the outside, and that's per an RUS standard. And we also like to have that 2-aught extend out beyond the gate swings. So if you draw it in your CAD drawing, kind of the swing arc of your fence gates, you need to have copper 2-aught out beyond that gate swing. Even if you spec it for the contractor to install it to swing inwards, you don't know if somebody, if it truly gets installed that way, or if somebody misses that, or later they add it and change the gate and make it swing outward. We just always design it so the gate can swing out and still be safe. And you want to make sure that, that's all modeled in your study. And then we also model the fence post, all the fence posts as ground rods because they get tied back in. So your fence acts like a bunch of ground rods as well. So that's basically it. Now we know what information do we need on the front end to gather, to have on hand to be able to actually do our grounding study. The next module, we'll talk about how to perform the grounding study, how to optimize it, and how to actually mitigate the touch and step potentials with copper in the ground and rock layers and any other aspects that we may use and adjust to make the site safe.